We'll give just a couple of seconds for people to join in, and then we'll go ahead and get started. All right, let's get started. Good afternoon, everyone. On behalf of the Association of Transportation Professionals of Indian Origin, ATPI in short, welcome to today's webinar. The topic is reducing the carbon footprint of concrete, challenges and opportunities. And our speaker today is Dr. Tom Van Dam from Nichols Engineering. Next slide, please, Prashant. Okay. And greetings from Austin, everyone. My name is Salil Gokhale. I'm the president of ATPIO. I'm joined by my good friend Prashant Ram from Applied Pavement Technology. We're part of this non-profit organization called ATPIO. We've been around for quite some time. And before I hand it over to Prashant, just wanted to say, first of all, a big thank you to Tom for doing this webinar today, and also to Aptec for hosting this webinar. And just a little bit about our organization. This is the third webinar that we are presenting this year. I'm very excited for today's topic. And about ATPIO, we're a nonprofit organization. Our mission is to mentor young transportation professionals, foster collaboration between academia, private and public sectors. And the big vision is to assist and promote transfer of transportation-related knowledge and technology between our two countries. So welcome to today's webinar. When you do get a chance, please look up our website at atpio.org and also on LinkedIn. And I'll hand it over to Prashant to introduce Dr.
All right, thank you, Salil. So today's webinar, Salil mentioned the topic. It is all about reducing the carbon footprint of concrete. And this is a very, very timely topic today. You might have seen the announcements from the White House. And in general today, there is a lot of emphasis on moving towards greener energy sources, greener materials. And I won't say anything more. That's what we're here to learn about from Tom. But I'm not going to give you a formal introduction to Tom, as many of you might already know him from other interactions with him. So I'm going to tell you three things about Tom today. So the first time I actually saw Tom Van Dam's face was on the Michigan Tech University's webpage about 17 years ago when I was applying for grad school. I was looking for professors to work under, and I saw that photo on that webpage, and I thought, oh, this is a person I never ever want to work with. That photo was really scary. So what the lesson learned from that was, first impressions are strong, but they are not always right. So I've had the opportunity to work with Tom a lot over the last 15 years, pretty much my entire professional career that I've had. And then I've gotten to know him a lot more closely through the project that I've worked with him on. And he was the one who introduced me to the topics of environmental sustainability and climate change. And for that, I am forever grateful to him. And Tom refers to himself as a recovering academic. So as you see his presentation, you will see why he refers to him as that. So I won't take any more time. So without further ado, I'm going to turn over the screen to Tom and let him take over. So Tom, the screen is yours.
And let me make sure I find the right one. I think it's that one. How's that looking? Is that the right screen, Prashant?
Yep.
Good?
That's good.
Excellent. And yeah, I forgot about that, Prashant. When I had my faculty picture, I don't like pictures of myself. And so what I did is I made a really, really mean face. That was my official faculty picture. And apparently it scared Prashant, which probably did him a favor, because then he went on to Purdue and he actually had good faculty other than somebody like myself. I'm going to talk about a topic, obviously, that's very, very, I'm very passionate about, very important to me, very important to, I think, many people, and very important to the world, and that is our need to reduce the carbon footprint of all of our materials and everything that we do, but for my work, specifically concrete. So let's see if I can get it to advance. There we go. Excellent. So these days, climate change is really at the forefront. Politicians, come and go, but we have scientific facts remain. The Arctic is melting, sea levels are rising, hurricanes and wildfires becoming more severe. Biden administration, as Prashant alluded to, is really emphasizing climate change and the need for carbon reduction. Recently, they passed the Infrastructure Investment and Jobs Act, the IIJA, and most recently, the Inflation Reduction Act. Both of these major acts include a very large set aside of money to basically advance this idea of carbon reduction, and even specifically things that affect concrete. So these low carbon solutions are really of increasing interest to governmental agencies. They're of interest to industry. They're of interest to individuals. And this is not just a US effort, as you know, this is a worldwide effort. So folks that focus on domestic politics within the US are missing the bigger picture, that this is as important here as it is in Europe, as it is in India. So climate change, I really feel compelled to go through a number of slides here, depending on the audience, to demonstrate why this really matters. Changes in the global climate are occurring, and they're due to humanity's activities. This is supported by historical observations and physical climate modeling. Optimistic models looking forward predict substantial climate change over the next century. And the rate of change is going to be dependent on what we do as a species worldwide, and that these greenhouse gases that we are emitting today, they have a very slow feedback function in the atmosphere, and they are driving climate change. And even if we change our ways today, we're going to see these effects at least till 2050. The certainty is spelled out in the IPCC 2021 document, summary for policymakers. It's unequivocal that human influences have warmed the atmosphere, the ocean, land. Widespread and rapid change in the atmosphere, ocean, cryosphere, and biosphere have occurred. This is without question. The uncertainty really lies in how the future will change, depending on uncertainty within the models and in the uncertainty of what we do. And so if we look at some historic data, the warmest multi-century period in more than 100,000 years has occurred in the last 50 years. And this warming is unprecedented in more than 2,000 years. And so if you look historically at the reconstructed data for the last 2,000 years, you'll see a fairly flat, actually we're in a bit of a cooling period from the 1500s, and just within the last 50 years, this tremendous spike. And if we focus in on that spike, and then we factor out the impact of the greenhouse gases that we've emitted into the atmosphere, you see that the track would have been the same by models, that if we factor in natural solar volcanic activity. The big issue here is, since we started pumping carbon dioxide and other greenhouse gases in the atmosphere, we've started to see this dramatic increase in temperature. If we look at those averages, they take us to about this point right here. And depending on what we do going forward, if we keep business as usual, we are going to see dramatic, almost 5-degree change, average change in 5-degree centigrade change into the future over by 2100, which would be absolutely devastating to the world's ecosystems and to humanity. If we even do modest changes or fairly aggressive changes to try to reverse things, we'll get here to just under a 3-degree centigrade increase. And what we're really trying to focus on is about 2-degree change. And that's going to require some really, really significant efforts. If we look at that 2-degree increase in global average temperature, models would predict basically the entire globe is warming. Certain areas are going to be very dramatically affected, and that's the North Pole in particular, is or the northern part of the globe The Arctic is definitely suffering right now. Permafrost is melting and a lot of negative impacts. Moisture-wise, it's a hit or miss. A lot of areas are going to get drier. Some areas significantly so, such as in southern Africa, the southwest of the U.S. Predicted droughts. India is looking at parts of it are going to get wetter. And so India will be getting warmer and wetter, and with that higher humidity and higher temperatures, again, it's going to be a very stressful on the population. And also, some of this water comes in other things, as we'll talk about momentarily. The likelihood of sea level rise, it's already rising. Most estimates are placing it under a meter, which will still be a very traumatic effect on a lot of the world, a lot of the coastal areas. But in some, the low likelihood, high impact storyline, basically we get ice sheet instability, we could see 1.5 or more meters of sea level rise, which again would be devastating to coastal areas in which most of the world's population resides. So all depends on regional differences, temperature, salinity. I think that the key element of what has happened recently is we're seeing much more flooding in coastal areas that it's even sunny day flooding, where there is no storm, there is nothing other than all of a sudden, like Miami is starting to see flooding occurring in other coastal areas in the US and elsewhere in the world. But then also what we just saw recently with Hurricane Ian in Florida, where these storm surges can be, is really the most devastating effect on people and property. And so this just shows a map of Florida. If we see a modest, the lowest projected sea level rise of under 1 meter, a lot of Florida, southern Florida, is going to find itself really underwater. And so this is not just this is not trivial. This is why a lot of places like Miami are building seawalls to keep water out. And then the final big impact is droughts, wildfires, extreme storms. I lived for years in the the Southwest, Reno, Nevada, Las Vegas, Nevada. The wildfire situation in California and the West in general is extreme. And then these extreme storms where the extra energy that's been put into the ocean and the atmosphere from the heat it's not that we're going to have more hurricanes or typhoons. The ones that we're going to have are going to be larger, higher wind velocities and much more damaging. And so all of these combined factors present a challenge. And so really the challenge in front of us is change is difficult. We all know this. It's very difficult to make people do something different than what they've done before. Focusing on cement and concrete, these are carbon intensive industries, and we'll talk about that traditionally. And then the way we design, the way that we specify materials are dictated by the past. They're dictated by what we know, what others have done before us, and it leads to a conservatism in our codes and specs. We have life safety issues, of course, that we must adhere to, and it just makes it much easier not to change our behavior. But I feel this is an opportunity, and the opportunity, and it's exciting, is we are allowed to get out of our rut, to embrace some of these new technologies, a new way of thinking about things, and really change our behavior, the behavior of our industry, and therefore the impact on the world, which is a nice place to be, to actually have an opportunity to make a difference. So the hope is we have a lot of new policies and initiatives that are focused on sustainability, and in particular carbon reduction. A lot of these fall under a broad umbrella of the Buy Clean initiatives. The cement and concrete industry is focused on change. This is true of the North American Cement and Concrete Institute. This is focused on the European cement and concrete industries, and throughout India and in Asia. So Portland Cement Association has a net zero by 2050 commitment. I know the Cement Association of California, Nevada, they're focused on 2045 net zero. Other organizations, ACI, ASTM, and others are embracing the need to do this. And then associations that represent the trades, like the American Concrete Pavement Association, American Public Works Association, American Society of Civil Engineers, and others, as well as nonprofits like Breakthrough Energy Foundation, are all embracing this need to have this big, hairy, audacious goal of let's get to net zero by 2050. And so what can we do? And the answer is there's quite a bit that we can do. And what we're doing right now is a step in that direction. This is educate ourselves. Take in peer-reviewed, good information, learn, read, question, and then move forward. Educate yourself. It's really important to have life cycle thinking when we approach this problem. Short-term solutions, easy answers. Oh, we just need to do this thing, and that's all we need to do. It's not going to get you there. We have to think long-term. We have to play the long game. We have to use materials wisely. We have to think about that next concrete mix design that we do, or the next structure that we're designing or having built. Bringing things not just from the time that the materials comes out of the ground until we place it into a form or finish it on a grade, but beyond that, and consider the whole life cycle of our structure. And then verify. In the end, it's really important that the things that we do, we adopt some type of a systematic, unbiased verification that's done according to standards to make sure that what we're doing is actually doing good and not doing bad. When we think about life cycle, the main thing is think of the circle of life. You know, we start with design, let's say, and we work ourselves through material acquisition and processing, construction, operations, whatever, if it's a pavement, if it's a building, whatever it is. How do we preserve and rehabilitate the structure? How do we get the maximum amount of life out of it? At the end of its life, how do we reconstruct using the existing building or structure as our raw material for our new one, and then cycle that back into design? And so there's a lot of all along here. We're not going to have time to cover each of these phases. There's a lot of good documentation out there, but you know, just keep in mind all of these things are important. Now, circling back to really the topic for today, which is hydraulic cement and concrete mixtures, and I call it hydraulic cement, which primarily we're thinking Portland cement. This is the most common building material on the planet. Humankind uses about a cubic meter of concrete per person per year. It's an immense amount of material is used, and it is not an exaggeration in the least to say civilization is built with concrete. Foundations for houses, water treatment plants are made with it, port facilities, pavements. You can hardly think of a civil engineering structure that does not contain concrete as an essential element. But as a result of this massive use of this material, 5 to 8% of the global greenhouse gases produced every year are from the manufacture of Portland cement and concrete. The large economic, environmental, and social impacts of this material in the US, we make about 89 million metric tons of cement annually. We're almost now kind of at our steady state maximum, where we're now importing about another 10% into the US economy right now. It's linked to approximately 1% of the greenhouse gases emissions in the US. If we look worldwide, what you'll see is the big user of concrete is China. Roughly 57% of global cement production occurs in China. The second largest is India at 7% of the global production of cement, whereas US is down around 2%. So You know, the big fear here is, and this has been written up in a number of papers, is as India continues economic development and growth, that they will follow the Chinese model. And all of a sudden that the Indian production of Portland cement will balloon, and it'll become a much bigger contributor to global greenhouse gases. And we'll get to some things that are going on in India momentarily that are actually a bright spot to avoid this problem. Why is cement such a big deal? We can go out, we can dig a hole, we can mine limestone, we can mine clay, shale, process it, get it ready to feed it into a kiln, and that's only about 1.5% of the total greenhouse gases associated with the production of that cement or that concrete. 89%, almost 90% is from actually burning those raw materials in a cement kiln. 37% of that is from the fuel being used, but 46% of all of the CO2 associated with a cubic yard of concrete at the gate of a concrete plant is from taking that limestone, converting it from calcium carbonate to calcium oxide and CO2. And so a tremendous amount of CO2 is being liberated from burning limestone. Once we make the cement, now that's over 90% is just in the Portland cement. Only 9.5% of all of the rest of the CO2 associated with that cubic yard of concrete is from at the gate, is from making this concrete itself. Net result is for about every pound, kilogram of cement made in the US, about 0.94 pounds of greenhouse gases are liberated, almost all CO2. So we take that cement, we mix it with gravel, sand, water, obviously some admixtures, and at a typical concrete at the gate in the US, we have about 310 kilograms of CO2 per cubic yard. 275 of that is from Portland cement production. So when you look at those numbers, you know where the focus needs to be, and that focus needs to be on Portland cement and what we can do. So the Portland Cement Association, being very, very bright people, they understand that this is something that they have to grapple with. And they have come out with their net zero by 2050 initiative. There's many parts to it. I'm going to just quickly talk about a few of them, but they fall into a clinker optimization, cement optimization, concrete optimization, and then in-service and end-of-life carbonation. So those are kind of four of the big pillars of what they're doing. And I'll talk about each of those individually a little bit. But the plan is definitely something worth looking at, and it's something mirrored in Europe and elsewhere. You know, so how can we reduce greenhouse gases during production? Obviously, we can go into super efficient kilns. We can look at high efficiency grinding mills for grinding clinker, gypsum, and SCMs and other blended materials, limestone. We can look at waste fuels, and ultimately maybe plasma, if we can get lightning in a bottle and have something like fusion or an abundant source of clean, free electrical energy. But remember, this is only 35, 36% of the total greenhouse gases associated with that, with making concrete. The other thing to recognize is because we're basically calcining that limestone and driving that CO2 out of the flue, you have about 25% mole volume of CO2 in the exhaust gas of a cement kiln. That is a great place to grab CO2. It's a great place to sequester CO2. And the plan in California right now, I can tell you, is I think by 2035, they're expecting to have operational sequestration going on 1 to 2 of their 7, I think they have 7 operational cement plants right now. And worldwide, this is already being done on an experimental basis and will largely be brought about throughout the world. Again, understanding where are we getting the electricity to do the sequestration, and what are we doing with the sequestered CO2 are issues that we still need to solve. When we move to cement optimization, this is about replacing that Portland cement clinker that we got out of the kiln with other things. The most common other thing is a supplementary cementitious material. In the US, that's most commonly fly ash, but it could be fly ash and other things. This can happen at the concrete plant, or it can happen at the cement supplier who does the blending. A second thing that we can replace with is limestone. In the US now, with ASTM C595 type 1L cement, which many of you are probably seeing in your markets if you're in the US, basically you can intergrind realistically 12. I think some are pushing it up to now 13%, 13.5% interground limestone. It works very well together with an SCM, and we'll talk about that. So we can start to reduce the clinker content of that cement, and that's the way to really drop that clinker factor, or the kilograms of CO2 per kilogram of cement. Supplementary cementitious materials include fly ash collected from the flue gases of coal burning power plants. Less and less of these plants are becoming are available in the US and elsewhere, obviously because of the switch away from burning coal. We have slag cement is another source where we can take ground granulated blast furnace slag and grind that up, and it creates an excellent cementitious material. And then natural pozzolans, calcined clays, volcanic ashes, ground pumice, other sources of natural material that are naturally pozzolanic that with some processing can be used. So these are the common ones that have been used. These days, there's a lot of interest in alternative SCMs. ASTM C618 is starting to expand its definition of what is going to be an acceptable pozzolan for use in concrete. Reclaimed ash that's mined from landfills or ponds is one really major source of potential pozzolan, and this is already being done. We often have to process this. We have to dry it. We have to burn out some carbon on occasion. We have to do some grinding to make it work, but it seems to work well. More uses being considered about ground bottom ash, ground glass, and then there are some specially prepared pozzolans that are being looked at that are even sequestering CO2 in the process. And so all of these are being investigated and more are being sought. The blended cements that I referred to, they have been around for a very long time. The type 1L was added, I believe, in 2008. This is very common in a lot of the world, very common in Europe to buy a blended cement. I've spent quite a bit of time in Africa, a bit of time in Central America, South America, where it was very common to buy your cement already pre-blended. But it's in general not a very common thing to do in the US, but I think we're going to see more and more of it. And so if you can work with a ternary blend of a limestone with a pozzolan or a slag, these can be very effective because the sulfate balance can be handled by the cement supplier, and we can have a very workable product. There's also a lot of interest because clinker is so energy intensive and so carbon intensive to look at alternative cementitious materials. These can include some that we've already have commonly used: calcium sulfoaluminates, calcium aluminates, magnetic phosphates are all cements that have been on the market throughout the world for a long time. Many of them are very fast setting, but they are often very costly. So I know these are from a price point, they are not something that can easily enter widespread use. Non-traditional blended hydraulic cements. One of the ones that the world is very excited by is LC3. Even if you want to see a really interesting video on this, just Google Wisconsin Girl Scouts LC3. And these Girl Scouts, led by a woman named Julia Porter, they did a fantastic job on LC3 talking about it. This is a blend of Portland cement, calcined clay, that's of a lower quality than like a pure kaolinite, and limestone. And on the right kind of shows some figures that represent the LC3 type of formulations that can occur. This is something I was talking to Prashant a little bit about. He said there's already a couple of cement plants in India that are in full production with LC3. And it is a possibility of using, common abundant materials to reduce that clinker content by 50% or more of our cement, which is a significant step in the right direction. A lot of individuals are very excited by alkali activated hydraulic cements that are still hydraulic, but we have no clinker. So you could take a fly ash, like a low calcium fly ash, and you can take that and basically, a high calcium fly ash class C or a slag cement, and activate it with an alkali activator, and you'll get a hydraulic reaction that will form similar hydration products to Portland cement hydration. Another alternative is geopolymer, which, where did that go? Okay, I want to go there. A geopolymer, which is a completely different reaction where, again, we hit it with a highly alkali environment, some kind of an activator that to raise the pH of the solution. That will lead to dissociation of the alumina and silica chains that are in some glasses, and these will then start to polymerize. This is, again, not a hydration reaction at all, but a polymerization reaction that creates a very, very durable cement and concrete. So these are available. I mean, runways have been built with geopolymers. Alkali activated hydraulic cements are on the market as some high-end specialty materials. Calcium sulfoaluminate cements are commonly used as a very, very good rapid set repair material. But there is no scenario that exists in which a sufficient amount of alternative cementitious materials exist to replace the versatility and the availability of Portland cement. So we can nibble around the edges and we can make some inroads, but we're not going to solve our problem likely this way. So what can we do today in a practical sense is one thing is use a low clinker cement. And the second part then is to use less cement. And the best way to use less cement is put more aggregates in our concrete. There's been some excellent work done by a number of researchers. This shows something called the tarantula curve by Tyler Lay and his group at Oklahoma State University. It's one way to proportion aggregates. This is for a paving mixture, but he also has another curve for pumpable mixes. And with this, you can easily take mixes and pull a mix that might have 564 pounds, 611 pounds per cubic yard of cementitious materials. You can pull out 50, 60, 70, 100 yards of 100 pounds of material, cement, out of your mix. There's a common fallacy, and I see it time and time again, that more cement in a concrete means more strength. And it's simply not true if a mix is properly proportioned. And I'll put a caveat on that right now, and that is if you need higher strength and you're in a uninsulated type of environment, the additional cement will help your early strength because the extra heat of hydration will speed things up. But there are other ways to address that. This just shows some work that was done by Peter Taylor and Wilson at Iowa State University for a given water cement ratio, fairly low at 0.35, different cementitious contents, and you can see almost no difference in strength at different times once you get past about 500 pounds per cubic yard, once we have enough cementitious material to fill the gaps between the aggregates. That's a lab study. This is a project that I worked on in Las Vegas, Nevada. It's called Project Neon. It was about a $750 million I-15 reconstruction job right through downtown Las Vegas. And this is real data collected on that project, where we looked at a 500 pound per cubic yard mix in contrast to the DOT's mix, which is a minimum cementitious content of 611 pounds per cubic yard. And what you see in this data is effectively almost no difference between the higher cementitious content and lower, little bit at 3 days, but look at the time frame when this was done. This was, even in Vegas, this is a cool time of year, but by the time we get to the summer and things really start warming up, it's almost the same. Maybe you could argue at 3 days, a little bit more strength with the higher, but by the time we get out to 28 days, one, astronomically high flexural strengths, and two, almost no difference. As a matter of fact, statistically, no difference in strength between 500 pounds total cementitious and 611. These both have 20% Class F ash, same water cement ratio. And so this is a clear indication that real concrete being placed on grade in multiple places around the country are being placed with very low cementitious content. And so the walk away here, the takeaway is, if we increase the amount of SCM or other additives to replace clinker, so like an LC3 system or a blended cement system or blending at the concrete plant, and we use optimized aggregate grading to reduce our cementitious content, we can dramatically impact and reduce the amount of greenhouse gases associated with our concrete. This is a very, very important point. So if we get into something like in service, one other part of the PCA plan that's very important is carbonation. And I think what we have to realize about carbonation is, we talked about the fact we took limestone, we put it in a kiln, we burned it, we created calcium oxide, and we released CO2. Well, that CO2 is out there. It wants to get back together with that calcium oxide, and it will over time in a concrete structure. So the concrete structure begins to carbonate. And the picture on the right shows basically a concrete specimen that's been slabbed and stained with phenolphthalein, and you can see the carbonation front in this specimen. This is a pavement, that's a joint, and so you can see how we got some carbonation. Everything that's not pink has carbonated. And this is kind of typical for a pavement, what we're seeing here on the right. And so this paper by Anderson et al., it's a great paper. It does talk about how CO2 uptake occurs, how we're converting the calcium hydroxide to and CO2 to calcium carbonate, and it uses Fick's law, the assumption in the paper, and depends on the exposure and quality of concrete. And so if you are in a dry environment or an area that has periods of a lot of dryness, so maybe between monsoons, for example, and you have concrete that's fairly porous, you will see a very, very high degree of carbonation. And so a roof tile in a place like Africa, or possibly, through other places in the world, it is going to really go through a high level of carbonation. If on the other hand, we have very high quality concrete that's underground, concrete that's kept wet, you're going to see relatively low carbonation. And I'm going to do a little illustration here on just a typical US pavement to demonstrate maybe how this could work in a model and when we think about the life cycle. And so basically a standard 4,000 PSI concrete pavement, a 6-SAC mix, 564 pounds per cubic yard. If we do the calcs, we're going to find out over something like 50 years, we may see roughly 14,000 to 20,000 pounds of CO2 is carbonated per lane mile of that pavement. That's about 700 to 1,000 gallons of fuel consumed, which is not a heck of a lot, but it's not nothing. And it would look something like this with the higher quality concrete carbonating less than a lower quality concrete. One thing I wanted you to think about, though, is in this case, if we diamond ground that surface. So let's say after 10 years, we diamond ground it, ground off the carbonated part, exposing fresh paste. What you will see is the carbonation reaction will resume. And what that might look like is with grinding every 10 years, we're going to end up sequestering a heck of a lot more than double, almost triple the amount of CO2 that gets sequestered in that concrete. On the other hand, if our choice of a fix in this case was let's seal the concrete up with an asphalt overlay, we basically ceased carbonation. And this actually talks a lot about concrete block, right? If you're looking to sequester CO2 and you paint your block, you're not really going to get much carbon sequestration there. Why I think this is interesting is if we looked at the amount of CO2 that it would take to grind, and we look at what diamond grinders consume over a lane mile of pavement, we almost end up being carbon neutral with that diamond grinding. So even though we're expending fuel to grind that surface, it's basically coming out flatlining at a net zero with the amount of extra carbonation that would occur. And the thing that we're not talking about is the add benefit of the smoothness. So if you look at the HDM4 pavement models by the World Bank, or the National Cooperative Highway Research Program 720 study, or work at MIT, or by NAPA, what you will see is a direct linkage between fuel consumed by vehicles operating on a roadway and how smooth they are. And if we can smooth out roadways and keep them really smooth, we're going to have a tremendous amount of savings. Now, coming up on the last topic here, which is assessment. And this, in my opinion, is probably, after education, is maybe the most important thing. There is a lot of greenwashing going on throughout the industry, throughout a number of products. Everybody's got green products. And this emphasis is going to become more and more so as more and more money and initiatives are being brought about to reduce our carbon footprint. We must adopt the use of standardized assessment to know that we are doing the right thing. We have to be able to look at an LCA, a life cycle assessment model based on ISO standards that is to assess what changes we have made and what they really mattered. And so on concrete, what's going to be happening more and more so is you can request an EPD. So you can have your baseline mix, and some producers in the US are already doing this. You can request an environmental product declaration that was developed using rules that were established by a very rigorous process. And then that was to execute a life cycle assessment. And they can tell you basically with those rules, how many, how many kilograms of carbon dioxide are in that cubic yard of concrete. And then we can pull some of the levers. We can reduce the clinker content. We can reduce the cement content. We can really find out what that reduction looks like to the point of placing it on grade or placing it in a form. Definitely stay informed, seek help as needed, ask questions, involve yourself. But this assessment is moving along, and we're going to see more and more of it happen. And I always tell people who know me, this is one of the few times that I have probably the only time I have a picture of Ronald Reagan in a slideshow. But trust but verify is one of his famous statements, and that's exactly right. Listen to what people are saying, but verify. Take these assessment tools. A number of them are becoming available to you. Product declarations that are done according to rules can be trusted within a certain category of product. So if that category is concrete, you can compare those if they're done according to the same rules. FHWA has a tool out called the LCA PAVE tool. It's going to be undergoing a fairly significant facelift here soon, and that'll be available. In California, they have a tool that's going to come out very soon. That came out, but I think they're redoing the data on it right now, called LCAP. And then if you're into pavements, there's the Athena Pavement LCA tool. There's EC3 is a tool that's available. And so there's a lot of ways for you to come up with this information. And I would challenge you to start looking into it and figure out how to do it. Just a really quick current initiatives that are going on that are very exciting. This end of July, early August, Minroad paved a new test site with 16 test cells. They featured some, a conventional control, and then a whole number of different other alternative material types, from those that sequester CO2 at the plant to those where CO2 is sequestered within the SDM, to some alternative cements, to alternative SCMs. And so this is going to be monitored here over the next couple of 3 or 4 years. And we'll learn a lot about how these materials performed in a real project. We also are working on a study with Breakthrough Energy Foundation on identification and elimination of barriers that exist within our codes and standards, and really within our industry and our aversion to risk, and how we can address that as we change. The support of Breakthrough Energy Foundation has been amazing, and the amount of partners that we're able to work with to help with some of these Buy Clean initiatives has been, it's really changing the way that we're doing things. And then there are many other federal, state, local agency efforts, too many to really list. A big thing is the FHWA Climate Challenge. We have $2 billion has just been designated within the Inflation Reduction Act to go to state DOTs to help them implement EPDs. So this whole area is about to get turned on its ear, and we are going to see a lot of activity here. So in summary, sustainable concrete practices are available for all concrete structures for all phases of life. My bias in the slides probably came through a little bit on the highway side, because that's the pool that I swim in, but I do a little bit of commercial work as well, and it's completely applicable to buildings, warehouses, public workspace for sure. Sustainability requires a life cycle perspective. So every time you're making a decision, make sure you keep that life cycle in mind. I will tell you the most unsustainable solution is the one that fails right after you do it. And I've been involved now with 2 interesting paving projects. One of them a plastic pavement that recycled plastic, even though it wasn't really recycled, but a plastic binder replaced the asphalt binder in a pavement. It failed within a week in that particular project. And then recently one with a alkali activated cement that we could never place it. Now, it doesn't mean that those products in and of themselves are bad, but they weren't very robust for that application. So make sure you keep that life cycle perspective as you move forward. Strive to optimize your cement and concrete. When a spec comes to you, do not just push back sometimes. I push back on so many specs all the time, and I will tell you most of the time I will get overruled. I feel like that guy pushing that stone up a hill, but don't give up. Keep pushing back, keep trying to do the right thing, and every once in a while, like on Project Neon, you can be successful. Learn about the tools available to you for verification. Avoid greenwashing. Do start to look at if EPDs are available and whether you can request them, if for no other reason than for educational purposes. And then really, I think I'll circle back on one of the first things I said. Yes, we have challenges, but at the same time, this is really exciting. This gives us a chance, especially as we bring on young engineers, to get them involved, to get them excited about what we're doing, to realize we have a part to play, not just in creating safe, infrastructure, durable infrastructure, but infrastructure that actually has a role to play in reducing climate change. And I think with that, I'm pretty much done. And I think I hopefully have some time for questions. Yeah, I went maybe 4 minutes long from what I thought I would. And so Prashant, I'll turn it back over to you.
All right, thank you, Tom. So we do have a few questions. I think a few of them I'm going to ask you, and then a few from Salil. So maybe I can just get started with one of the questions I have. The first question is really about the diamond grinding study that you were referring to, and people were asking if you could share the source for that particular study. If you can put it in the chat box.
The source is me. Basically, you know, it's just calculations that I've done using the equations, and people have looked at different elements, and I think it'll be looked at more, and I'll probably be found out to be really wrong, but I don't think so. I will tell you that in my work, I've done a lot of petrography, so we look at a lot of carbonation depths within concrete pavement. We typically just see that 4, 5, 6 millimeter depths. And then when we look at a diamond ground pavement that's been out there a while, we again see that 4 or 5 millimeter depth of carbonation. So as long as we can expose the surface of the concrete. So what happens with carbonation is when we do that conversion from calcium hydroxide to calcium carbonate, it's pore filling, right? The calcium carbonate fills more space than what was originally filled, and therefore it closes off the surface, and that's why Fick's law works. So it only goes to reckon when you mill off that carbonated surface, you've reopened it, you will get that carbonation will occur. So I challenge anybody to go ahead and run the numbers and let me know what they find, and if I'm wrong, then I'll do my next one and I'll talk about all the crow I can eat. Wouldn't be the first time.
All right, thanks, Tom. So Salil, I believe you had a couple of questions.
I do, and actually it's what kind of a follow-up on what you just said, Tom. The question is, will sequestration through carbonation cause carbonation-induced corrosion?
So will a sequestration, in other words, carbonation of concrete, will it cause what?
Corrosion.
And that is an exceptionally good question, and is one of which it's absolutely could. You know, we rely on the high alkali environment of concrete to protect embedded steel from corrosion through the formation of a passivation layer. And what happens is if that alkalinity drops, which would happen in carbonation, the passivity layer breaks down and corrosion can ensue. And so without question, if we are thinking in our minds of somehow making concrete to purposely sequester CO2, and it's a reinforced structure, we're really asking for problems. So back to my example of a masonry block or a roof tile, not such a big deal, right? We should not have embedded steel in those structures. On the other hand, a reinforced steel column that does not have steel protected from corrosion, we certainly do not want that concrete to carbonate. And I will also add, though, if you drop that water cement ratio below about 0.5, which you should be doing for structural steel, the level of carbonation is pretty small. And there's other people investigating how we can carbonate the concrete when we recycle it. So this is all a very active area of interest in research. So you can spin yourself around. But yes, that was a very observant, it was a good question.
And moving from the concrete microstructure to a higher level, Tom. So we have a lot of materials out on the market today, right? You know, a lot of them advertising themselves as low carbon, carbon sequestering. Carbon is in the name of almost every other new material that comes up today. And you have these new materials, and then some of them, I don't know, what are your thoughts on how cost prohibitive they are? How do we make some of these materials more competitive with traditional Portland cement-based systems, if in fact that is an issue?
We are in a time of change, right? That our traditional materials that we've become very familiar with and are comfortable with, Portland cement concrete with fly ash, are either not going to be available or are going to become pretty carbon intensive. We're going to have to do something different. And you are correct. Everyone's jumping on the bandwagon. So the first thing, Prashant, is back to Ronald Reagan: trust but verify. So when you see a product advertising something remarkable, you could trust in a sense, or you can be skeptical, which is what I am these days. And so what you should ask for is EPDs. If someone says, hey, you know, we have this new product that's going to reduce your carbon footprint by 80%, say, oh man, that's fantastic. I'd like to see your environmental product declaration showing that. That'd be the first thing. That being said, we will start to use new materials. We're going to have to educate ourselves. These new materials can work, but they are going to require us to do things differently than we used to, and there will be a learning curve. So I would never introduce a new material into a critical life safety structure. Like, don't, put it in a column, a beam, the most important structure in your inventory. I always tell agencies to use the maintenance yard parking lot. It's a good place to start to try out a new material. So the idea is keep learning what others are doing and develop your own in-house experience by working with these materials. And the industry overall, researchers and those who are on code writing committees, they are all acutely aware of what needs to change. So the codes are changing, the specs are changing. Like I said, you're going to see, if you've been observant of ASTM-C 618, spec for fly ash and natural pozzolan, it has changed actually in fairly significant ways over the last 10 years. And what I will tell you is it will continue to change. And as it changes, it's going to recognize more the performance of these materials and less prescriptive, more performance-based. So all I can tell people is we're at the kind of the cutting edge. We're right at the beginning of this process. It's a great time to be active. It's a great time to be inquisitive, a great time to try things out. But please be cautious, yet open. I know that seems contrary, but you have to be both. I don't know if that even came close to answering your question, but I do think we are in an exciting time. A lot of opportunity exists, and be open to it, but do check. And use your boss's patio for trying your first placement.
All right, thank you, Tom. Salil, I believe you had one more question.
Yeah, one more question seems to be repeated. Tom, what is a good resource or a place that students or other academics can go to for researching more on this topic? If there's a list of peer-reviewed publications or articles or any other resources that you might recommend.
The first thing I will say, and I probably didn't have it in here because I was trying not to talk about pavements only, but if you are into pavements, the FHWA Sustainable Pavements Program, and you can Google it, it's got great data. I mean, it's got great information. Some of it that I've been involved with, Prashant's been involved with, others at AppTech. Kurt Smith was the program manager for that for AppTech and did a great job with that. The whole program is getting a little old in the sense of 5-6 years old, but it's still great information. So that's one area for sure that you can go to for very reliable information. The American Concrete Institute is very active in this area right now. They have a new center called NEW, N-E-U. So the new center, I believe, will be also a good source of information. The NRMCA, the National Ready Mix Concrete Association, has a number of good practical publications and guidance on this. And then also, I'm forgetting somebody, I'm sure that will get mad at me at some point. PCA, I mentioned them, their effort on the net zero 2050. So what I would suggest is if you have a specific question, please do feel free to reach out to me, or Prashant again is, I appreciate him asking me to talk, but he's also very knowledgeable on this topic. You can reach out to us and we could try to direct you to the best sources. But it is something, do keep your eyes on what's going to happen with the MnROAD data. We will start publishing that data. And again, Prashant is involved in that project, as am I. So we will publish those results as soon as we can.
Excellent.
Thank you, Tom. Just we have 1 more minute, maybe 1 or 2 more questions. So one, again, big picture question. So do you see Portland cement being extinct in a couple of 100 years?
No, actually, I don't. And I say that because I think Portland cement, it is an incredibly versatile, robust, relatively inexpensive material. Do we see it getting more expensive? Yes. I think because we're going to have to grab the CO2. What's going to have to happen is we're going to be just basically grabbing the CO2 out of the back of the cement kiln and then using it as something useful, maybe aggregate. I don't know. So I don't see it becoming extinct. I do seeing it being, supported by a cast of characters. So I think as engineers, our life will become a little bit more challenging. But back in 1976, or let's take 1979, when I started my university career as a student, concrete was cement, water, aggregates, maybe a water reducer, maybe an accelerator, maybe a low range water reducer, maybe a little bit of fly ash. But I remember my first concrete class, I was kind of like, who in the heck would want to use fly ash? This stuff is so variable. It just causes you problems, right? Now look at concrete today. I mean, it's actually a fairly complicated system, and we've adapted. And so that's where we're going. We're going to have to continue to adapt. We're going to have to educate. And, like I said, I'm excited by the opportunities. I think it's going to be more complicated, but it's also going to be, at least less damaging to the environment.
Thank you, Tom. So that's all the questions I had. So Salil, did you have anything before you close out?
No, I think no more questions, but I do want to say a big thank you, Tom, for taking the time. This was a great presentation, and I really enjoyed it. Thank you so much.
I appreciate it. And I do want to mention, one of my best trips I ever had, I went to India with Sunil Vanakar. Some of you might remember Sunil at FHWA, and we did a week-long trip, and we hit, oh my gosh, I think 5 cities in like 6 days. And it was wonderful. The food was great. The people were great. But I hope if I ever get back to India, I could actually see something other than the inside of an auditorium. So hopefully, my wife would like to go.
One of us and we'll hook you up. Awesome. Thank you so much.
Take care.
All right. Thank you, everybody, for attending. Good day.
Thank you, everyone.